welcome. Love Closure West. Love being here. Earlier in my career, and this has happened multiple times, so I'll just give you one story. I did, man, that light goes on, you can't see anybody. I did,
You're getting very bright.
I did some embedded programming, and the particular project was to capture license plates with video cameras, analog video cameras, and there was a card that we used that plugged into the machine that would capture the video, and then I wrote drivers to talk to that card and capture and do stuff. So after I got my code mostly written, I was probably 80% through the project, the European Union decided to outlaw the manufacture of electronics using lead-based solder. And so that card was discontinued. And so I had to go back and hack up my code to use a different card, a different video capture card. The problem was, the problem why that arose was because I did not use an abstraction of a video card. I hard-coded to that particular card. Another thing that happened, this story is on my blog, closure.net, is I did an implementation of miniCanron a long time ago. David Nolan did an excellent job with CoreLogic. He did a real implementation. And so I was sitting around one day after I'd learned about monads and some other things and was just kind of thinking, and it's like, it hit me that I could redo the miniCanron search engine, search stuff, by changing the monad. I can make it a parallel search instead of a linear search through the hierarchy. And that was possible because monads are an abstraction, and miniCanron is built to that abstraction, not to a particular search strategy. And so by switching out the monad, it was possible to do a parallel search to the search space rather than a linear search. So you can check out the longer explanation on my blog for those details. But the magic part of that is miniCanron is built on top of an abstraction. So as a result of these experiences, and many more, I've really come to value abstractions. And what we have in functional programming is, so in object-oriented programming, which most of the world uses, as you know, your abstraction is the object. And then as I started to use functional programming and get more into it, we have so many more abstractions that we can take advantage of in Clojure and in functional programming than is really possible in object-oriented, because we have first-class functions. I'm sure all of you are familiar with the conj, C-O-N-J, function, and that is an abstraction in Clojure. It lets you abstract away the idea of adding an element to a set. And you just call this one function, and no matter what kind of collection, not set, no matter what kind of collection you pass into it, it will just stick that one item into the collection. So that's one abstraction that was very common in Clojure. And as I go through this, we'll see some others. This is a survey talk. I'm not going to go into deep dive in any of these abstractions. So keep that in mind. Also, at the end, feel free to ask questions, and we can talk about the other things that I may have glossed over. So, also, there's going to be a lot of vocabulary that's going to sound really weird, because a lot of it comes from category theory. So just don't freak out. Alrighty. So first of all, Clojure, a Lisp on the JVM, as we all know. In Clojure, you have all these things. If you have a list, you can concat two lists together. And if you concat an empty list to a list, you get that original list back. You see some other things up there. These are all abstractions or instances of an abstraction called a monoid. And a monoid is simply a data type, a list, a set, or whatever, a number even, a function that will combine two of those data values together to produce a third combined function, a combined data value of some sort, and a zero value. Not zero in the arithmetic sense, but zero in the sense that if you combine that value with any other value, it leaves that other value unchanged. So hash map, you can merge two hash maps together. Sets, you can union them together. The interesting one, which didn't really occur to me until I'd actually came across a reference to it in a paper, is function composition is a monoid. You can take, using the comp function, you can take two functions and put them together to get a third function. I mean, it's standard closure programming. And the identity function is the zero value for that monoid. So that's all a monoid is. And it's a really useful concept so that you can think of, as you're building your program up, you can think of composing functions to get your end functionality that you need. Or you can think of composing sets or whatever. And instead of having to use, say, okay, well, I'm using a set, so we're just going to use a union, you can say a combination function. And I've put out a library. No, I haven't put out this library yet. I intend to shortly. A protocol-based library to have a comb function that will combine two data values properly. So that's monoids. Now we get into the fun stuff. Functors. That big fancy word sounds a little scary. It's really not. It's just a context data type. A simple functor data type would be a list or something that's seekable. So a functor is a context data type that wraps other values, and a function that's typically called fmap that will take a function of one argument, a generic function, and apply it to the values that are wrapped inside that context data type, and return, then fmap will return another context data type with the result of mapping that other function on those values. Closure's map is just this. Now Closure's map only works for seekable data values that you can do sequences on. Fmap is more general than that. Your context data type could be a function. You could have a function that every time you call it, it just gives you a value back. And then you can you can map the other function on top of that value and then wrap that into a function. We'll see some more specific uses of that type of thing. But that's all a functor is. So if you're going to do a mapping operation, you're using a functor. A subcase or a subset of functors are applicative functors. This is where it starts to get a little bit interesting. An applicative functor is a context data type, and then you have two functions that operate on that data type. One that wraps a value in the context. So with just the generic functor, you're just given the wrapped values. You don't have any way of creating them yourself. So they have to come from somewhere. But with an applicative functor, you actually have a function that wraps any given value into this context. And then you also have a function which I'm calling amap that applies a generic function of one argument to the functions that are inside, or to the values that are inside that wrapped context value. The interesting thing that occurred to me is juxt is just an example, an instance of this applicative functor. In particular, it's the reader applicative functor. Now, the reader is where you have, let's see how to say this. Well, okay, I'll just look at the equivalent down below. You have a reader, which will wrap a value inside the reader applicative functor. And in this case, it's just a list. So, or it's just the function list, not a list. It's the function list. So you take a list, you put it inside your reader context, and then you hand that wrapped list function to amap, and then you hand it a list of functions. And those functions are defined because they're in, you can think of them as being values in the reader applicative functor, as they are functions that take an environment and read something from that environment in order to produce their result. And so I'm just taking advantage of keywords being functions as well. So those are three functions, A, B, and C, that take your environment, read the value out of a hash map, which is your environment. Your hash map, and your environment does not have to be a hash map. It can be any value, but in this case, it's going to be a hash map. So it's going to pull those values out of the environment, and then the list function that is passed to AMAP. AMAP is going to unwrap list. It's going to apply the A, B, and C to your environment, and then it's going to aggregate those values into a list. So that's all Juxt is. Juxt is a particular instance of an applicative functor that we see in Clojure. But you could, if those functions A, B, and C were always returning integers or numbers, you could substitute, instead of list, you could substitute plus in there. And you would get a single integer or a single number back as the result of applying AMAP to A reader plus ABC. So that's all an applicative functor is. It's a way of doing effectual side-effecting functions in sequence, composing side-effecting functions. And that's the whole purpose of the applicative functor paper, which I highly recommend reading. And there are papers for all these things that you can turn up with Google searches pretty easily. But applicative functors are just a subset of functors. So then a subset of applicative functors are the famous monads. So a monad is a context data type, which is, and then, like we've been saying before, then a function that wraps values, similar to what an applicative functor has, and then a function bind that will apply a function to the wrapped values. A note I need to make, the function to wrap the values in a language like Haskell, where you have static typing, you can just use a function like return. And in the applicative functor, it's called pure. And the type system will figure out which, in this case, which monad return should result in or result. In Clojure, we don't have that static type system, so we have to cheat a little bit. And instead of having a single function that will stand for all monads, you have to use like list or set or hash map to stand in for those things. But in the case of monad, you have that kind of function, and then a function called bind, which will take this wrapped value, say a list, apply a function, which bind takes as a parameter, to each item in that list. So it'll unwrap your wrapped value, get the values out of it, apply a function to it, get those back, and then do magic to flatten the collection. And eventually return a wrapped value that's in the same context. So there's a funny thing on the blog that says a monad is just a monoid in the category of endofunctors. What's the problem? I'm kind of coming to the point where I understand most of the words in that sentence. I still don't know quite how they all plug together. So, list comprehension, the for statement, or the for macro in Clojure, is an example of monad comprehension that we use all the time. Do, seek, and the rest are also variants of this. But you can have monad comprehension on other monads, like a set monad or a state monad. So the idea of comprehending a data value, a wrapped data value, is more general than just list comprehension. And that's the idea behind LINQ. Any query language, not just database queries, or SQL, but any query language, graph databases or column-oriented databases, anything you query and get a set of results back, the semantics of that query is set monad comprehension. And that's the whole thing, the whole reason, that's the whole foundation of what LINQ is built on, is that all query languages, you can query objects, you can query databases, you can query other stuff, they're all set comprehensions in the set monad. So, going off on a little tangent here, I thought was kind of interesting, so I get to throw it in. You have some tables there on the left, people and colors. And they associate people with a group and groups with colors. And then a little SQL statement where you select from name and color, or you select name and color from a join of people and colors with a where clause. And you get the results you see there. So standard SQL. Even I know that much SQL. So now, if you're in just straight closure, and you define a set on the left, a set of hash maps that have name and group in them, and a set of colors, and then do a list comprehension. Get each person out of the people, each color out of the colors, a little when clause, and return a hash map. You get the same set of results as you did with the SQL. You're just doing it with a for statement, list comprehension, which you could use set comprehension there just as easily. The only difference between list comprehension and set comprehension is the set comprehension removes duplicates in your result. You could wrap the for in a set, a call to set, and it would give you the same thing. So for those of you familiar with core logic, define a relation, people, using cond, define colors, run that core logic query, and you get the same results. So at a fundamental level, there's an equivalence between query languages, monad comprehension, and logic programming. And it's all based on, logic is the foundation of all those things. So these are all equivalent. There's an equivalence underneath there. And I am not sure what really magic stuff you could do with that kind of equivalence, but I've got some ideas floating in my head, and at some point I'll write a blog post about them. But there's something cool here. I don't know exactly all the ramifications, but there's something cool. There's a project called Berkeley's Orders of Magnitude, and the idea is that there is a way to write distributed applications using orders of magnitude less code than what is commonly used. And the guy, Joe Hellerstein, came up with the Calm theorem, which says, logically monotonic programs are guaranteed to be eventually consistent. So that means that if your program and your data structures are logically monotonic, in other words, that you're only adding value to your data structures, that you can distribute those over multiple machines, multiple threads, whatever, and after all the message passing gets done, you will have a consistent answer spread across your set of nodes. It's really pretty interesting. They invented a language called Bloom, which is a language for writing those types of things, and they're based on Datalog, which is a recursive query language. And they have some interesting ideas about time, which is, made me think of Datomic and the way Datomic handles time, and so it really seems like that's where things are going. People are starting to realize the importance of time, and values in the past that were true may or may not be true now, that kind of stuff. So given the equivalence I just showed, would it be possible to write distributed apps with core logic? I believe there's already a connector to let you query SQL databases in core logic. So could you write distributed applications using this abstraction of monad comprehension and guarantee their, the eventual consistency? And that's kind of the area that we're working on at Llama Cloud. So Bloom L, they extended Bloom to include something called a semi-lattice. And there's the Basho guy, I can't think of his name, did a talk at Recon on semi-lattices. Also called them conflict-free replicated data types, or CRDTs. And a semi-lattice is just a set of values that you have in your data type, a join function, and a special value that is less than all the other values, which sounds an awful lot like a monoid. And in fact, in a specific thing is a commutative monoid, which doesn't mean the order doesn't matter in your combination. So here's another place where this abstraction pops up and gives you some tools to think about distributed applications and how to use them, how to compose them out of smaller abstractions. Alrighty. So that was kind of a tangent under monads. So you have comonads. Now, monads were a subset of applicative functors, which were a subset of functors. Comonads are not a subset of applicative functors. They are a subset of functors, though. So a monad, or comonad, is a context data type, again, because these are all functors. They all are context data. They have a context data type which wraps other values. In this case, one of the values that are being wrapped, it has the focus. That's what you're kind of working with. And then there is a generic function, extract, which will extract the value that has the focus out of the wrapped collection. And then extend, which is a function that takes a wrapped set of values and another generic function that will, the other function will take a wrapped value and return just a plain value. And so extend takes that function and shifts the focus to all of the wrapped values that you have in your original value, calls the given function with each of those wrapped values with the focus shifted, collects all of the plain values back out, and then wraps them up again into the comonadic context, and that's the value that gets returned. So that's all kind of hand-wavy stuff, but some practical things that we already use are like zippers, Huey's zippers, to let you work with trees in a functional way, very efficiently, good stuff. Reactive extensions, what Eric Meyer has done. Eric was responsible for link. He also is responsible for reactive extensions, RX. And the stuff that Netflix has done with the reactive extensions for Java is pretty stinking cool. But that's all based on the comonadic idea. So that's another place the abstraction pops up. Cellular automata, like the game of life. That's a really clear example of a comonad. So you have a grid. That's your comonadic value. You have, they have values in the cells. You have rules of how to determine when a cell in the next generation is going to be alive or dead. And you apply that rule to your current generation. So that's the extend operation. The function that applies the rule is a function that takes a graph and returns, has one of the cells that has the focus and returns the value of that cell in the next life by looking at its neighbors. So it has to have the context to look at. So it needs the whole value. That's the whole point of comonads, so you have the whole value to look at to extend it. And so extend is just the function that applies the liver die function to the current generation to generate the next generation. So cellular automata, either one-dimensional, two-dimensional, n-dimensional, whatever, is a really good example of a comonad. Also, in the paper that introduced comonads by Kieberts, he mentions that objects are comonadic. I've got to ponder that a little bit. That's why it's not on the slide. I need to think about the ramifications of what that exactly means, but it's a pretty cool idea. If objects are just another instance of an abstraction. And then it may give us some ways of using objects inside Clojure. We'll see. Alrighty, so arrows. This is the last abstraction. So arrows are also a subset of functors. And you can't see it here, you'll see it in a second. But all monads are arrows. All comonads are arrows. And then other things are also arrows. It doesn't make sense to use arrows where you can use monads or comonads because the notation for those guys is cleaner than what arrows are, than the notation for arrows. But it's interesting to see that they are special instances of arrows. And there are some places where arrows are exactly what you need. So an arrow is a function, and we keep talking about a context with other values embedded in it. Well, an arrow, the context is a function, and the value embedded in the context is also a function. In other monads or whatever, you could embed like just numbers or strings or something inside a context. Well, in arrows, what you embed inside the context always has to be a function. And since it's function embedded in the context, then you want to compose those. And so seek, which is just a function that composes two arrows front to back, so that the output of one goes into the input of the other, and then the output of that is the output of the composed arrow. And then a function inf that applies an arrow function. It creates a new arrow that wraps the given arrow function. And that new arrow takes a vector of inputs, or not a vector of inputs, takes one vector as an input and applies the arrow that's inside, the function that you're wrapped inside, to one of those values, producing a new vector with the result substituted in for the original parameter. And John Hughes wrote a paper generalizing monads to arrows, which is the basis of this. Fascinating paper. It took me 5 times to read it, and I couldn't even understand it until I implemented one of the arrows, which is the streams thing. So we have storm, you see Cascalog, and the like. Those are stream processing abstractions, which are arrows. So if there was an arrow library, which I hope to release one soon, you could implement storm or other stream processing things as arrows. The other motivating example John wrote in his paper is parsing. There's a problem with recursive descent parsers where they hold on to the entire text that you're parsing, and so they're not very space efficient with large texts. Using an arrow, you can implement an LL1 grammar, which will use one character look ahead to efficiently parse the text, and it's able to discard the text that's already parsed if it knows it's not going to need it again because of the look ahead. So that's another example of arrows. Alrighty, and those are all the abstractions that I'm going to cover right now. But this is how they kind of relate together. You have all of Clojure. Monoid type abstractions are one thing, and then functors are another. Starting off with map. Then subset of functors is applicatives, monads, arrows, comonads. You can see how they kind of relate together. So I'm just beginning my investigation of a lot of these concepts. I've done monads. I'm pretty comfortable with them. But some of these other things, I'm just now starting to investigate them. And there's a hint of really immense power, I feel like, in these things. I haven't figured it all out, but I'm excited by what these kind of concepts will allow. One of those is the ability of composing your application out of small pieces of abstraction and lifting your thinking above the level of, well, I've got to do this to this value and this to this value, and I've got to do it in this order, and here I need to keep track of this mutable state, or I need to simulate mutable state, or whatever. Lifting your thinking above that mundane level. I think there's a quote by Dijkstra saying that abstractions are not, I'm going to butcher this, but are not to let you, hide, or they are to let you hide details, but not to let you speak imprecisely about, one level, but they allow you to speak precisely about a level above that. And so that's what I think abstractions really buy you. And that's what I think studying these types of things, even though they come from category theory and they have strange names, my hope is, over the coming months, hopefully not that long, is to get blog posts out about each of these in depth and eliminate some of the uses of them and how they can make our lives easier. So that is the end of the talk part of it. So questions, as soon as I can see you guys. Well, okay, let's see if I can explain this. The question was, how do reactive extensions and FRP fit into the comonadic idea? So you say you create a future, and that future embeds a value in it. So you extend that future, and so the future is your comonadic value. It embeds a computation inside of it. So you extend that future with a function that checks to see whether that future has timed out or not. And I know that functionality already exists in futures. You can give it a timeout when you dereference it. So you can extend that future value with a timeout checker. And you can extend that with some other functionality that takes account of the whole future. Like you can pull that value out of that future and do something with it and have that computation be in a future. So that you can start up these futures, you can compose compositions inside futures and never dereference them, and just have them spawn other futures, like read from a database, be done in a future. Then you extend that future with some processing of the data you got, then extend that future with generating some HTML, and then extend that future with sending that HTML back to the client. And so your main thread that actually gets the request in just spins up all these futures on the side and doesn't have to worry about dereferencing any of them. So that's a pretty hand-wavy explanation. It's all I got right now. As soon as I dig some more into that, I'm going to write it up and give some really serious details, because I think there's some cool stuff there. I'm also interested to hear Alan Dijkwert's talk later about FRP. And I've talked to him a little bit about it, but I'm interested to see some more, get some more knowledge about FRP and how it relates. Okay, so lifting occurs in a lot of these abstractions. You lift functions into your abstraction. You lift functions into your monad, lift functions into your arrow. And what that means is you take a function and you do some stuff to it so that it can be used on values inside your monad or inside your arrow or and the like. So that's kind of what lifting is. Okay, so the comprehension is the do notation, is what they call it in Haskell. And you're familiar with for. You have for, and then you have a binding vector. And that binding vector has a symbol and an expression. So that's the do notation for monads. If I've read the papers right, and I haven't implemented these, so again, it's on my list. In a comonad, all the arrows are reversed. That's one way they talk about comonads. So you'd have a codo, say, then you'd have a binding vector, except instead of having a symbol and an expression, you would have an expression and then a symbol. And so that symbol would then be fed into the expression, which would produce in the next line of your binding vector, those results coming out of that first would be given a symbol name, which would then be fed into the next expression. And so it'd be reversed. Your binding value would be reversed. And then you have a final value that would give you the result. With arrows, you have branching things. It's easier to describe visually than it is verbally. But arrows, remember, are a subset of monads and comonads. So you would have an arrow do, and then instead of a binding vector where you have pairs, you would have triples. And so you'd have symbol, expression, symbol, and then symbol, expression, symbol. And you could use symbols from the previous steps in later steps, and then it would do some parsing magic to figure out all the networks of things. So that's how I see, when I read those papers, how I see them coming up with notations that are similar to for notation or comprehension notation in monads, as kind of a similar thing with arrows and comonads. It's actually an area of research of what's the most effective way to notate these operations. So there's still some flexibility there, and people are kind of arguing over which is which makes the most sense. But that's my reading of it so far. Man, you're really putting me on the spot. Because I hate to admit this in front of this crowd. Is datomic queries more like a comonad?
Or writing this.
And I hate to admit it standing up in front of you guys, especially with who is in the audience, but I've never used atomic. Yeah, I know. So I really can't answer the question. I don't really know. Buttonhole somebody that knows what they're talking about as far as datomic goes, and maybe they can help you. So they were crazy mathematicians. I don't know what they were doing. I believe so, yeah. I think, what time is it? 11:30. I think we're over time. So thank you guys. If you want to talk about it more.